We are just about ready. We have one more kind of big push through angular momentum. And then on Tuesday, we'll solve the hydrogen atom. All right, we'll do the radial problem on Tuesday, which I will kind of skim through because the math is, again, somewhat complicated. It's not that important. What we really care about as chemists is what do we learn from it. Which is why I've been focusing a lot on the angular part because, again, what we saw when we dealt with the angular wave functions, the angular behavior of our electrons around our proton, we got the orbital structure that we want, that we know from GenChem, S, P, D, F, G, H, I, J, K, right? And we saw that these have to do with how much angular momentum and also the direction at which the orbital direction of the electron is spinning around the proton. Right, so the angular information encoded in an atom really defines the properties of its atom. We'll find that the radial part just ultimately determines what energy scale your electron is at, whether it's really excited, has a lot of energy, it's far away from the proton, or if it's close, right? Difference between valence and core, right? Of course, core and valence, when we talk about valence electrons and core electrons, of course, they play a huge role in chemistry, but again, those properties arise from having many electrons. When we talk about a valence shell or a core electrons, that usually means we've got at least 2 or 3 or 4 electrons. Of course, that matters in chemistry. But when you just talk about the hydrogen atom, we don't really need to think about valence or core because the electron is the valence electron. There's only one. And the thing that really defines the behavior of the hydrogen atom is it's the angular properties of the electron. All right, of course, the radial part does matter, but we'll see that I think it's important to note that the angular part is more important. So what I introduced last class, the end of class, I kind of rushed through it, but we'll talk about it today. Very important is this idea of determining how can we measure many things for our system. Like sometimes we don't want to measure just one thing. We identified an angular momentum. We wanted to measure the magnitude of angular momentum, L squared, how fast it's rotating, and we also wanted to measure the direction. Right, that's 2 things we have to measure. Right, so we got to make sure that we choose a wave function for our electron that allows us to measure both of them. Okay, and so I came up with this postulate. Well, I didn't come up with it. This is the postulate for it, which is our test for whether 2 measurements can be done simultaneously on the same wave function, which means that both pieces of information are simultaneously measurable, and they don't affect each other. So we use this commutator relationship, this square bracket between our 2 operators. Right? You can consider these operators A and B to be anything you want: position, energy, angular momentum, color, flavor, you name it. And the idea is that we're going to measure these 2 properties consecutively on the wave function. So on the left-hand side we have AB. If the wave function goes on the right-hand side here, so if we apply a wave function to it, right, we're measuring it for the wave function. Put the wave function in there. This part of the formula, we're measuring the B property first and then measuring the A property. We get some value for that. Okay. And then we do the opposite experiment where we measure A first, then B. We get some result. And then we calculate the difference between the 2. Okay? So we get a difference of results depending on the order of our measurements. And if we don't, it's equal to 0, we say that these operators commute, which again is an algebraic thing. A times B is equal to B times A. But the important result of that is that we can always choose a set of wave functions, some representation for our system that allows us to get information about both properties. Right? There's a representation for our system that gives us information about both A and B. But if we find that when we measure the commutator for our system and we get a non-zero result, which means that they're different by some amount, that guarantees that there is no set of wave functions that we can come up with that allows us to simultaneously measure both properties without affecting the system. Okay, so the reason why I bring this up is I'm not interested in calculating commutators so much, but I think it gives you kind of a mathematical structure for what do we mean by things that are simultaneously measurable. It means that the operators must commute. They must look like normal algebraic functions as you know and love, right? Because in algebra and calculus, I don't think you ever learn non-commutative math in those, right? Every algebraic operation you do in that class is commutative. You can always flip the order, algebra and basic calculus. But my point is that there are algebraic structures in the universe. Say the algebraic structure of operators, which are just functions on a space of something that represents a measurement of some wave functions or some vectors. These don't have to be commutative. There are elements of algebraic elements that don't commute with each other. All right. And because each of our measurables can be related to some sort of algebraic operator, that means that there's going to be two classes of operators. There's going to be ones that commute and ones that don't. And this has deep consequences on what we can and can't measure at the same time. And I kind of talked about this at the end of last class, which is that we wanted to measure the length, the magnitude of angular momentum, how fast it's spinning, plus its direction, how it's orbiting the proton. Is it precessing around a pole, or is it precessing around the equator? And the fact of the matter is that what I said is that we can only determine one direction. We can only know one direction. So there's three of them, of course. It's a three-dimensional vector, angular momentum. We can only know one of the three. And what that means is that when we look at the commutators for the operators that correspond to our directions, we'll find that the commutators are not equal to 0. So let me give you some examples. I gave you some examples last class, so these are kind of a refill, but I think it's good to go through them again. And some of these things we've just assumed implicitly about quantum mechanics so far. The first one I'm going to write down is one that we've already taken advantage of over and over in this class, which is that when we take the commutator between position and energy, right, can we find a set of wave functions for our system that allow us to measure the position and the energy simultaneously? Well, we've been doing that the entire semester. Right, we've been solving wave functions with the Schrodinger equation, right? We find wave functions that satisfy the Schrodinger equation for H, and then we're measuring X on it all the time, right? We did that in homework 3, we did it in homework 2. So this is equal to 0, right? We've implicitly assumed this, that we can measure both of these simultaneously, and it's 100% true. It's not hard to show this, right? And this just says that we can write wave functions. Right? All this is saying is that there are wave functions for systems that have fixed energy and defined position. Well, right? This is why we write, for instance, this is why we can write things like this, psi n of x. Right? We come up with wave functions that are a function of the position. There we go. Right? That's literally the fact that we can write these wave functions in terms of x implies that the commutator between these two operators is 0. If it's not, we couldn't write psi of x because we can't measure x and energy at the same time. Right? So that's good, right? This is a nice sanity check that we're doing the right thing. And today, last couple of classes, maybe a more relevant example right now is measuring the magnitude of the angular momentum, L squared, and one of the directions. Right? And this is also 0, right? And we showed this because remember the solutions, the wave functions that satisfy the equation for L squared give us the spherical harmonics, which are functions of m and j. Right? The quantum numbers for each of these operators, m and j. So we can measure both of those because our wave functions are defined as both of those, with both of those. Right? Wave functions, so psi here for angle, theta phi, are equal to our spherical harmonics, where j is the L squared quantum number and m is the LZ quantum number. Right, so these functions are encoded directly with the information from both of these operators. Right, they tell us something about the direction and the magnitude. Okay. If these were not equal to 0, we'd never be able to write these, right? But there must be some class of operators that fail this, and there's quite a few. And let me just give you some examples. I can kind of give this to the last class. We proved this, that x and p, momentum and position, are different by IH bar, the commutator. Right? So this says that if I measure the position and then my momentum of my object, and then flip the order of those measurements, the results of those two experiments are different by a complex factor. H bar has units of angular momentum. I means that it's in the complex plane. And so what that means is that when you measure x and p, and then flip it, the result is different by some phase angle, some rotation in the complex plane. That's what IH bar means. Right, so when you measure these, the difference between the end result of your system by measuring xp and then px, the difference is that your system has some arbitrary rotation in the complex plane, so now it's a different state. Right? You think about color, right? When we measure the flavor, if we define the color of our electron and then we measure flavor, the resultant electron is pointing somewhere else. Right? And that's the exact same thing here. Now, this IH bar is very complicated. Right? I don't want to go too deep into the consequences of this I here and what this means. But the idea is, again, that when you do this ordering of the experiments and flip it, you get a different state in the end, right? You've manipulated your system between these two measurements, and that's not what we want. Now, we can't calculate it just yet, but just from homework 1, I won't calculate the exact answer for this. But if you take the commutator of color and flavor, this is also not equal to 0. Now, the result of this is not defined because I didn't define what this comes out to, right? But it's not equal to 0, and you saw this, right? When you define the color of your system, then measure the flavor, and then measure the color after, you've lost information about color. Right? Your white electron goes into the flavor box and comes out a white plus black. Right? And this necessarily implies that color and flavor operators do not commute. We can't have a wave function for our electron that allows us to define both the color and flavor simultaneously. The last one I want to write, and this is the one that I'm actually going to show you in a physical demonstration of this property using a physical object, not a quantum mechanical object. Let me just kind of demarcate things a little bit, not to confuse. All right, one more I want to write at the bottom, and I wrote this last class, which is that if you take two directions and measure two directions of your angular momentum and take the commutator, your result is off by a difference in z. Okay, so what does that mean? When you measure the x and the y direction of your angular momentum, and then you measure the opposite, the difference between the final results of those two measurements is a rotation along the z-axis. I'll show you this explicitly with a die, with a d20. Right? You can do it with a three-dimensional object. Right? So the difference between, so what the idea is that when you measure Lx and Ly, and then subtract that from the measurement of Ly, Lx, the end state that you get from those two measurements are either is generally flipped 180 degrees around the z-axis. You've rotated it. That's the difference, a rotation along the z-axis. And this is true for all of them. All right? It doesn't really matter how I write this, but if I were to say, for instance, write Lx, Lz, I get IH bar Ly. And again, if I measure two different directions, no matter which one I choose, combination I choose, my end result is always going to be different by a rotation along the third axis. Okay, so when I measure two directions, I lose information on the third. This is why we can only measure one direction at a time, right? Because we absolutely have to measure the magnitude of the angular momentum because that's proportional to kinetic energy. Right? We need to know the energy of the system. That's the whole point of quantum mechanics, right? We want to solve for the energies of our system because that's what we measure. That's the thing that's conserved in our system that we really care about. So we absolutely need a wave function that's defined in terms of L squared. And the only other option we have is one direction, right? Because the moment we include two directions, we lose information about the third. And that's no good. We don't want to lose information about anything. So the only option we have here is this, the magnitude in one direction. Right? Which direction that is, whether it's Harry Styles or Zane, it's up to you, right? I'm more of a Harry Styles guy, so we'll let Z be Harry Styles. So let me show you how this works physically. All right? There is a slight conceptual and technical difference between a rotation. I'm going to show you this idea with rotations of a die. So a little conceptual difference between rotations and angular momentum. All right, what I'm going to do is I'm going to rotate this D20, by certain angles, right? Certain combinations of angles. I'm going to rotate 180 degrees one way, 90 degrees another way, right? These are macroscopic rotations of large amounts of angles. Right? We're moving across an entire circle or half a circle. Angular momentum, again, we can think of it as a rotation, but these operators actually measure infinitesimally small rotations. Right? So this says that if we measure the direction along x and z, our system will be at minimum infinitesimally changed along the y direction, right? It might just rotate by 0.00001 degrees. Could be anything, but it will change. Right? So these we call angular momentum generators, rather they're functions that measure infinitesimal continuous rotation of a system. They're differential, they're derivatives. Right? So it's small changes in angle. So what I'm going to do with the die is not a small change in angle. I'm going to do a macroscopic change in the angle, very large change in the angle. And we'll see that the math works out the same, but there's a slight difference between rotations and angular momentum in this way. Right? We're causing angular momentum is we're applying a force that allows the system to smoothly rotate in a continuous fashion, which is kind of the same as rotating. Okay, it's a slight difference, but the math is basically the same. Okay, so let me show you this idea. So here on the screen, got a D20. Right? And I'm going to write down the orientation on the board here of our initial D20. All right? So I'm going to have the 20 sticking straight out. Right, so our initial condition, so I'll write step 0, is a 20 in the center, an upside down 14. I really struggled writing these upside down in last class. I'm doing a little better today. A 2 and an 8. And then that's good enough for now. Okay, what I'm going to do is I'm going to apply a sequence of rotations to the system along two different axes. And then what I'm going to do is do the same operation again, but I'm going to reverse the order of my rotations. So let's define an axis system, because I need to figure out how I'm rotating it. So we'll just use the same one we've been using this entire class, which is z in the up-down direction. All right, so what I'm going to do first step 1 is going to be a pi rotation, 180 degrees, around the z-axis. And then step 2, we only need to do 2 steps. I'll do a 90-degree rotation around x. All right, and I also need to define which handedness I'm going to use for my rotations, clockwise or counterclockwise. Let's just keep it easy and make them both clockwise. Okay, so I'm going to do these steps first, and we're going to write down what the end result of the die is, what side of the die we're looking at, and then we're going to flip step 1 and step 2 around and do the same thing. So for the first step, I need to rotate 180 degrees around the z-axis, which is this one. All right, so I'm just going to rotate the die this way, in and out of the board. Oops, that's the wrong axis. All right, so the 20 is now pointing away from me. And as you can see now, I have a vertex in the center. So my end result for 1 is a 5-way vertex between 17, 7, 15, 12 upside down. That's not a 12. Sorry, I had it wrong. And a 10. Okay. So that's step 1. And now what I'm going to do is rotate it along the x-axis, which is this axis, right? So I'm going to rotate it this way 90 degrees. So that means this vertex is now going to be pointing straight up. Okay, so we're left now with this edge in the center with a 7 and a 1. All right, I'm not going to write any more than just a 7 and a 1. That should be fine. And it's an upside down one. Let's make sure that we have that. Okay. All right, so what we've done is by doing these 2 steps, we've gone from this 2014 edge to this 7-1 edge. Okay. So if these were commutative operations, and I flip step 2 and step 1, I'm going to take the 20, and I'm going to end up at 7-1. Shouldn't be dependent if they're commutative. But if they're not commutative, I should end up at a different end. I should end up at a different edge or side of the face of the die. All right, so let's go ahead and do that. So we'll reset our die, and we'll do step 2 first. I'll write it step 2 prime just to not confuse, and then we'll do step 1 prime, which is where we're going to flip these. So let's reset our die back to 20. I am failing my spot check at the moment. There we go. Okay, so now I'm going to rotate around the x-axis 90 degrees, so the 20 is going to be pointing up. All right, and I'm left at this 5-way vertex. Between 14, upside down, kind of a funky 4. That's a set 11, a 9, and 6, upside down 6. Okay, so if they're commutative, once I rotate this along z-axis, I should end up on the 7-1 face. So if I need to rotate around the z, I need to take this vertex and put it behind. Let me make sure I do this just right. There we go. All right, as you can see now, it's not perfectly 90 degrees, but we have now a new rotation. Right, now we have 17 and 7 and a 10 here. Right, so we've ended up now by commuting our operations to a different spot on the die than we were before. Right, this is all you need to prove it. They're not commutative. Right, I've taken AB, and then if you subtract BA, which is looking at the difference between this point and this point on the die, you can see it's not equal to 0. They're not the same. And it's not really that hard to show that to get from here to here, right, you need an additional rotation, and it's going to be a rotation around the y-axis. Right? Remember that the difference between, go back to the commutator, the difference between doing Lx, Lz and Lz, Lx is the difference in a rotation in y. Precisely exactly what we have here. We've done Zx minus Xz, and our end result is off by a rotation in y. Okay, so this is intrinsic to three-dimensional space. Rotations in 3 dimensions are not commutative by design. Not by design, just by nature. Not commutative. All right, so this is actually probably the first time you've ever seen this kind of math before. I don't know, maybe in linear algebra, if you've taken linear algebra, you might see non-commutative things. But the idea is that once you get to 3 dimensions, you actually, if you think about the algebra of rotations, how do you combine rotations together to create invariance, right? What were the types of rotations you can do that get you from one point to another point? And those rotations are not commutative by design. And this is entirely why we can only measure one direction. Because they're not commutative, we're always, when we measure 2, we're always off by the third. Okay? So it's not anything, the results of this in quantum mechanics, again, are a little more subtle than this, but the geometric source of the fact that we can only measure one angular minimum direction, and in fact, this is the entire reason, if you take spectroscopy with me next year, the entire reason why NMR spectroscopy works as it does. If we didn't have this, NMR wouldn't work. Right, so we can actually take advantage of this, but it's an intrinsic limitation we have, not because of quantum mechanics, but just because of geometry, just because of 3D geometry in trig. Any questions about that? Okay. I just wanted to say one more thing, is that you might ask, well, what about in 2 dimensions? Well, rotations in 2 dimensions are on a circle, and it's not hard to show. So if we're on a circle, 2-dimensional rotation, let's say we start here along the x-axis, and our first step is 45 degrees, step 1, and our second step is, say, a 90-degree rotation, 2, right? So we take this vector from here to here. What's the net change? Well, the net change is 135 degrees, which is either equal to 90 plus 45 or 45 plus 90. So it doesn't really matter in 2 dimensions which way you do it, right? 2-dimensional rotations are commutative, or commutative, excuse me. But 3 dimensions, they're not. The symmetry breaks down. Spheres have different symmetrical properties than circles. Circular geometries are commutative. Spherical geometries are not. This point was not lost on physicists and chemists. And there's a reason, this is one of the reasons why it took people so long to come up with quantum mechanics, because this idea of non-commutative geometry and algebra, no one in physics knew this until Einstein. Einstein started realizing that you needed to start thinking about this math, and a couple of other people, Poincaré and a couple of other major physicists and mathematicians in the late 19th century, said, hey, there are things that we don't understand in algebra, and they seem to be really important in science and the universe, 3-dimensional, how things work in 3D. And it wasn't until 19th century, late 19th century, they figured this out. Right? This is new math, which is why you don't learn it in calculus, because calculus was all invented in the 1700s, right? That's old math. This is new math, the idea of non-commutative algebra. Okay, so in some ways this is why quantum mechanics appeared so late, is that you needed to develop the math and promulgate it to get people to understand it, to then apply it to reality. And unfortunately, mathematicians don't always connect to reality. They tend to get lost in things. So the physicists had to learn this, and Einstein's one of the first people to really learn this. He also learns other things about geometry, and that's where general relativity comes from. Okay, so that's kind of all I have to say about this idea of indeterminacy in rotations in angular momentum. The idea is this is just something we have to live with because it's built into 3-dimensional space. But we can, as we'll see later on, as we'll see, we can take advantage of it. Right? There's unique things that we can pull from this indeterminacy. Okay. So we've kind of expressed mostly our understanding of angular momentum for our proton bound to an electron. Sorry, electron bound to a proton, right? That we have two operators that we can measure, magnitude and the z direction. These give us two quantum numbers, m and j, which determine, again, the orbitals that the electron is in. Okay? And so I don't really have much else to say about it right now because this is it. This is angular momentum in very basics, right? I'll just summarize it. It's like three equations, right? Angular momentum can be summarized in three different ways, three different equations in summary. That L squared applied to our wave functions for angles gives us h bar squared, and I'm going to erase my psi so it's a different color just not to confuse. Okay. Angular momentum gives you these eigenvalues, h bar squared jj plus 1, where j can be any number between 0, 1, and so on. Right? And then we have our direction operator, which measures the projection along the z-axis of our angular momentum. Which gives us h bar m. Sometimes we write it m sub j. Depends. I like m personally, just like m times psi. Right, where m can be any number between minus j and j. Okay. And our wave functions, of course, are our spherical harmonics. All right, and if we ever need to do any spherical harmonic math, like on a problem set, I'll give you the spherical harmonics. All right, they're just functions of angle. Nothing scary. Just some formula. And they're all tabulated nicely. That's it. That's angular momentum in 3 dimensions. 2 operators and a wave function. That's really nice. So the question, of course, is what else can we do with this theory? I've kind of reiterated over and over again that this is really, really important. And I want to show you, I want to motivate our discussion today. How much can we get out of this idea? Is there anything else we can learn using angular momentum? And I want to motivate it with an experiment. You're going to find that this experiment looks a lot like the color flavor experiment. And that's not a surprise because color and flavor are analogs for angular momentum, as we'll see eventually. So I want to talk about a unique experiment that was done many years ago. And where can I jam this? Oh, I'm going to zoom out just a bit. There we go. And I'm just going to put this over here in a nice big box. All right, so the experiment I want to talk about today, very briefly, is called the Stern-Gerlach experiment. All right, named after the 2 people who did the original experiment, Stern and Gerlach. Now, this experiment has been done 1.5 million times by 1 million different people. But Stern and Gerlach were the first ones to do it. And let me explain their experiment. Very, very simple experiment. So they take a gun that shoots out some particle. All right, and so here's my gun. And this gun shoots out, we're going to say it shoots out electrons, because we've been talking about electrons lately. Stern and Gerlach actually use silver atoms, but they have the same property. Doesn't really matter. And let's just say that this gun shoots electrons out kind of in a spread pattern. All right, they got this Glock on eBay. And what they do is they have this big pattern of electrons. So these are typically either You could do it with electrons. Stern and Gerlach did it with neutral silver atoms. Doesn't matter. The same result happens. And you can do it with any number of atoms. You can do it with anything, as we'll see. But originally it was done with silver atoms because that's what Rutherford used. It's a really good atom, really easy to make silver atoms, and they have really nice properties. Okay, and what they did is they want to collimate their electrons. So the electron guns are the same things that generate the light or the excitations in a old cathode ray tube television, old school TV. You guys are all probably old enough to remember to have CRTs in your life. But in behind, right, a CRT, the way a CRT works is you have this screen that has a phosphor on it, and you have behind it you have an electron gun that has basically a grid-like pattern, and depending on where you want to excite the colors and the pixels on your screen, you shoot an electron using an electron gun at the back of this tube to excite the phosphor at that point. Okay, so electron guns used to be a dime a dozen. You had at least one in every household. Nowadays, I think there's only one company in the world who still makes them. They're also used in other applications as well, but in TVs and cathode ray tubes, there's one Russian company or one Chinese company who still makes them. But you can buy them. And the idea is that they're going to put a wall in front of this gun with a little slit so that they only take the electrons that are moving straight along this axis. Okay, so they collimate this electron beam. And then what they're going to do is they're going to put it into a magnetic field. So they enter a chamber, a tube, if you will, that's magnetized. And I'm going to draw it by having two magnetic electrodes like this. All right, and one is positively charged, and the other one's negatively charged. All right, this is a magnetic field. Okay, so they put it into basically a quadrupole or some sort of dipolar magnetic trap, something you might find in a really old school mass spectrometer. All right, it's a tube that's magnetized. But the important thing about this magnetic field is that it's really crappy. It's inhomogeneous, which means that the strength of the field and the direction of the field is kind of random. It's not uniform. Okay, so depending on the initial trajectory of the electron, it might get deflected up, it might get deflected down, it might just go straight through. Right? It has lots of different trajectories. All right, so this is an inhomogeneous magnetic field, which is the opposite of what you have in an NMR. And NMR has the equivalent, but it's a homogeneous field, which means the magnetic field is the same everywhere in the tube, which is what you want for NMR. This is the opposite. You can think of this as a scatterer. This thing's using a crappy magnetic field to scatter stuff instead of focusing things. So these electrons get passed through here, and I'm just going to kind of just draw what we hypothesize their trajectories might be. Right? Some might come in and get deflected this way, some might get deflected this way, some might get deflected that way, who knows, right? Right, so these are the hypothesized trajectories. I'm just going to write that really small. All right, we don't actually know which way they're going to move yet, but the idea is that we're going to set the field up so that they move as randomly as possible out of the tube. Right? And then on the other end of that magnetic field, as they escape, we're going to put a phosphor screen, a detector, right? It's like a CRT. We have a detector here. All right, and I just want to make sure that the important thing here is that the axis of the field is the z direction. Okay, so I just wanted to write that really quickly. Okay, so if the electrons when they hit the detector, think of it as like a CCD, charge coupled device, right? Some sort of screen that lights up when the electron hits it like a bullet. Okay, so if the electrons hit up here on the north end, they'll light up here. If they hit in the middle, they'll light up in the middle, and so on and so forth. Okay, and so what I want to look at is when I do this process, what is the distribution of electrons on my screen? All right, so if you were to do this classically, all right, think of these as balls. The electrons as charged billiard balls. Okay, everything's macroscopic. and then you randomly move them through this, randomly scatter them with the magnetic field out, what would you expect to see on the screen? Well, there's going to be an equal amount of particles that scatter up and an equal amount that scatter down, and on average they're not going to scatter at all. Right? So the classical result, what we expect, classical expectation, is that we would see a distribution that looks somewhat like a normal distribution. Something like this. Right? On average, they go right down the middle, but there's some wings, right? Maybe the wings should be more dramatic than this. Something like that. Should go to 0 at the edges. Something like that. Okay. Right, that would be what you classically expect, right? That they're equal number north, equal number south, and on average they're just going to be in the middle. Okay, so what does Stirling Gerlach see when they push the electrons or the silver atoms through there? The actual experimental result is very interesting. So I'm just going to erase classical here, or expectation, so I can have some room. And then I'll write experiment here. Experiment, you don't see any in the middle. In fact, you see two lobes. It's a bimodal distribution that is centered around the edges, the two edges of the system. And that's not the best drawing in the world. I want this to be symmetric, so let me just fix that. It's a symmetric bimodal distribution, which means it has two kind of bell curves that are all centered at some... All right, it's kind of hard to draw this. That's a little better. Like this. And I just want to draw, so this is the center line of the trajectory right through the middle. And the distance from the peak here and the peak here are the same. Okay, so what that means is that on average, the electrons don't get deflected into the middle. They on average get deflected by the same amount up or the same amount down. There are none that come through the middle. All of them are deflected up or deflected down by roughly the same amount. So so that means that something clearly wrong, something different is happening here. Okay, so this is for hydrogen and silver, or not hydrogen. Well, hydrogen it works as well. You can do this with neutral hydrogen and get the same result. You get this for hydrogen, you get this for the electron, you get this for neutral silver, and so on and so forth. Right? Doesn't matter where you are in the world, what temperature you're at, how fast your atoms or your particles are moving. Doesn't matter if you've got COVID or not. Doesn't matter. Nothing matters. Doesn't matter. You get the same result everywhere. All hydrogen atoms, all electrons, and all silver atoms in the universe are the same, and they all show this behavior. Exactly reproducible. All right, so what happens when we change particle? All right, so what if we do this instead with, let me give you a better option, and this is what they actually followed up with. What if instead I use nitrogen, 14 nitrogen, so regular old nitrogen 14, this is just a normal nitrogen you know and love. When you do this experiment, you see a different pattern. You see peak at the top, you see a peak in the center, and you see a peak at the edge. Right? So again, let me just draw the trajectory axis of the electrons. So you see some electrons go straight through, and then you see 2/3 of them getting deflected in equal and opposite directions above and below the zero plane. All right, and if you ask the question, how many electrons are there in each of these categories? Well, in the hydrogen case, it's 50-50, as I said. And here you see 33%, and 33%, right? They're all split up equally. Right? You see three peaks. Let me give you another one. What I'm driving home is that it depends on the atom, right? It depends on the particle that does this. It's some particle-dependent property. It's not something unique to just electrons. It's something unique to this particle itself. If you do carbon-12, right, classic old carbon, you see no deflection. You just see a peak in the center. The carbon-12 atoms don't deflect at all. See 100% down the middle. All right, and I can keep going on, and depending on which atom you choose, you see different results. There are classes of atoms that split into 2. There are classes of atoms that split into 3. There are some that split into 5, some that split into 7, some that split into none, or just 1. All right, so it clearly is dependent on the periodic table. And I'm just talking about atoms here. It's much more fundamental than that. But look, we're chemists, so let's talk about atoms. All right, so there's something dependent in the atom that causes, right, so what is physically happening here? Something in the atom is interacting with the magnetic field to apply some angular torque to the trajectory of the atom, right? Newton's law says that atoms, right, particles that aren't perturbed continue on the same direction that they started in, right? All right, Newton's first law. But the magnetic field is applying some sort of angular torque to the trajectory, right? It's applying some sort of angular momentum to the electron as it passes through, causing it to deflect up and down. And it's not hard. And in fact, what they show is that they have curved angular trajectories. It's not like a hard, sharp jerk, but rather it smoothly moves along a circle, this deflection. Right? I can kind of just draw it nicely, right? Something that looks like, right? It has some smooth variance that you can inscribe along a circle. So you're imparting some angular momentum to these electrons or these atoms. All right? And what this is telling me is that hydrogen and silver, there are 2 angular momentum results. You can either bend the trajectory along one angular momentum, which causes everything to end up here. You can bend it down and end up here. And in nitrogen, you have 3 choices. You can either bend it down, bend it up, or it doesn't bend at all. Okay? So once you put all this together, you start to think, hey, there's something intrinsically angular about atoms and about electrons that is built into the particle and is specific to the identity. Right? Remember, these particles aren't connected to... We're talking about atoms here. We're not talking about electrons around atoms. There's no tether. These are free particles. They're not influenced by anything except for the magnetic field. And yet they exhibit an intrinsic angular momentum property. There are 33% of nitrogen atoms that, when putting through a magnetic field, have an angular torque to up, 33% to down, and 33% none at all. So there's something intrinsic about the atom that the atom always has this angular momentum. And even if you spin the atoms up, right? What if we did this experiment in a circle, right? Where they have defined angular momentum, you still see this splitting, the exact same splitting. Right? If you cause the magnetic field to be circular and you spin it through a magnetic field, they still deflect into doublets and triplets and singlets, exactly like this. So it's got nothing to do with the orbital angular momentum of the system. It's something intrinsic to the particle. So an intrinsic angular momentum that is fixed, right? It doesn't change. It's not like the electron around a proton where you can spin it faster and faster and faster, right? J can be any number. In some ways, it's like J is fixed. There's just 3 values of J for nitrogen, J, if you will, 2 for hydrogen, and 1 for carbon-12. There's some unique extra angular momentum built into the atom or the particle that doesn't change. It's fixed. So what is this? Well, I've been talking about it for the entire semester, so you probably already know the answer to it. But this is spin. Spin, or spin angular momentum, is this intrinsic spinning or intrinsic momentum. Every particle has a spin. Some particles have zero spin, but every particle you can assign an angular momentum to called spin that is fixed for the particle. Every electron has the same spin angular momentum as every other one. Every nitrogen atom has the same total angular momentum, spin angular momentum as every other nitrogen atom. You can't speed it up. You can't change J. It's just a fixed number. It's built into the identity of the particle itself in the same way that its mass is built into it, or its charge. Charge, mass, and spin are all separate and entirely fundamental. The sources of charge, spin, and mass all come from different mechanisms. How do particles get mass is different than how the particles get charge, which is different how particles get spin. But they're all intrinsic properties of every subatomic particle and every atom known to mankind. They're all separate, completely unique. Right? So when we look at a periodic table, as a physical chemist, I get annoyed because I get the number of protons, I get the electron configuration if I'm lucky, I get the mass, but I don't get the spin. But spin is just as important as the mass. Of course, as we'll learn, the electron configuration, actually the electron configuration doesn't even necessarily determine the spin of an atom. It's actually the nucleus that will also determine that. Because the proton and the neutron also have spin. Right? So the periodic table doesn't tell me these things, but it's just as important, it's just as intrinsic, and just as fundamental as mass. Right? You can see I have a bone to grind a little bit with chemists sometimes. Thankfully, there are chemists in the world who care about these things. So the question is how do we represent spin? Okay? And guess what? We use the exact same, we can use the exact same formula that we use for angular momentum. So how do we quantum mechanically treat it? Well, we're going to do the same thing. We're going to treat this spin as an angular momentum. All right, so how do we define angular momentum? Well, we're going to have two operators, one for the magnitude and one for the direction. So we're going to define two operators. All right, we have s squared, which is the magnitude of the spin angular momentum, applied to our wave function for our system, our atom, or our particle. And what's the result of this? Well, it's exactly the same as it was for angular momentum, h bar squared times a new quantum number, which we call the spin quantum number, ss plus 1. All right, but the difference here is that s can't be any value, right? Like j can. J can be 0, 1, 2, 3, all the way up, right? The electron can spin around a proton as fast as we want it to. S is fixed to the particle. It's a fixed number. So for instance, for the hydrogen atom and for the electron, for the proton, for the neutron, and so on and so forth, there's many particles. It's neutron 0. S is 1/2. Right? The electron is a spin 1/2 particle. For nitrogen, the nitrogen atom, and interestingly, we'll talk about this in a second, the photon and other atoms as well. These are the most common ones that I can think of. S is 1. Okay? And for carbon 12, S is 0. Has no spin angular momentum. That's why it doesn't get deflected by the magnetic field, because it doesn't have any angular momentum. So it just goes straight through. All right? It doesn't apply any torque to it because there's nothing to apply torque to. Carbon 12. In some ways, you can think carbon 12 to a magnetic field looks like a perfect sphere. Perfect sphere. Carbon 12 is just a perfect sphere to a magnetic field. But hydrogen and nitrogens, they have a funky shape. They don't look like spheres to a magnetic field. Right? And there are other particles, right? that have different spins. They can have all different ones. I'll just give you another example. Chlorine, for instance, S is 3/2, and so on and so forth. Okay, you can look them up on a table. It's not important. It depends on how many protons and how many neutrons and how many electrons you have determines these spins. Okay. There's some addition rules and stuff for these things. But we're not really worried about that. The fact of the matter is that every particle known to mankind has spin. Some have 0 spin, but you can always assign a spin quantum number to everything. And we need one more operator, right? We need the direction. So we define the S sub z operator, and the result is precisely the same. The h bar times an m number, which we call m sub s, times psi. And just like in angular momentum, m sub s runs from minus s plus 1 to s. All right, so it can run from minus s to s. All right, so m sub s, again, just like m sub j, m for angular momentum, determines how the electron is processing about some axis, right? How it's rotating. Now, you'll have to ask the question, now this is very odd, right? This is telling me that the electron, remember the electron's a point. It doesn't have any physical size. But the electron has some natural angular momentum to it, which means it's spinning on its axis. All right, so let's look at that for the electron in particular. All right, so S is equal to 1/2, which means that S squared is equal to h bar squared 1/2 times 3/2. Right, that's 1/2 plus 1. So 3h bar squared over 4. Right, and so that means that, right, so the length of that angular momentum vector for the electron is always 3h bar squared over 4. So it always has the same amount of angular velocity, if you will. The rotational speed of the electron is fixed about whatever it's rotating about in this way. And S sub z, the projection, can be anything between minus s and plus s different by 1. So the first value that's allowed for S sub z is minus 1/2. And then we add 1 to that, that's 1/2, and that's s. So there are 2 spin states for the proton, or for the electron or the proton, or any of these. They all have 2 spin states, plus 1/2 and minus 1/2. Once again, you guys know this because when you've been doing electron configuration and filling orbitals in GenChem, you've been putting a spin up and a spin down electron in every orbital. So that's just plus 1/2 and minus 1/2. What do these represent? Unfortunately, I can't draw something on the board that gives you a visual representation of what spin is. It is something entirely intrinsic to quantum mechanics. There is no classical analog to spin. I'm going to draw something on the board that is completely incorrect. I'll explain why. But it does give you an idea of how it works. And unfortunately, it just is not right. But it is the closest thing I can draw on a board that actually explains spin, at least to the level that we're comfortable with. So imagine you have an electron, okay, that's propagating along an axis. All right, so it's just moving in space. Okay, so it's just moving along in space. All right, think of it like, for instance, it's traveling along an electric field or down a wire. Of course, it's oscillating. It's a wave. So you can think of this electron propagating as a wave down this line. The 2 spin states determine, and this is wrong, but it's the closest thing I can give you, determines how the electron's wave rotates around the axis of its propagation. So while the electron rotates or moves along this axis, its wave function, which I will kind of draw something like this. Right, this is the wave function of that electron propagating through our system. Let me make sure I get the orientation right. This wave in time can rotate around this axis, right? It can oscillate in some helical fashion around the propagation axis, right? So there's going to be, it can rotate clockwise, right, around the axis, say the z-axis, right? So we can have rotation in the xy plane clockwise, or we can have counterclockwise rotation around this axis. And these can be assigned to plus 1/2 and minus 1/2. Okay, so the idea is that you can think of spin plus 1/2 and minus 1/2 as a polarization, a circular polarization of the electron propagation, right? Some sort of rotation of the wave. And one is right-handed and one is left-handed. All right? Or you can think of it as having plus or minus. It's the same thing. You have a plus rotation or a minus rotation, it's equivalent. However you want to think about it. Right? And when this interacts with a magnetic field, you have a magnetic field applying a torque in some direction. So if the magnetic field is applying torque in this direction and your system's rotating this way, right, they're going to work together. When they torque together, when you add the angular momentum of being applied by the magnetic field to the rotating object, they'll work together, or they can work against each other. Right? You can fight against the field. Right? So in a magnetic field, these will separate because one, you have addition of the angular momentum together, the addition of the vectors, and one, you have a subtraction of the two vectors. So they separate each other. Right? That's all magnetism is. Magnetism is just a differential response of spins to an electric field. Right? So one has a clockwise rotation, one has a counterclockwise. This is wrong. Because there's something very interesting that you find out, and when you deal with spin, not we have to worry about it, but I just want to tell you this. Imagine I take this electron now. Imagine that this propagation axis is on a rotating lazy Susan. Okay, so the electron is bouncing back and forth between the edges of this lazy Susan that's rotating. Okay, and so what I'm going to do is I'm going to fix the lazy Susan in place, allow it to propagate backwards and forwards, and then I'm going to cause it a 360-degree rotation. I'm going to flip the orientation of the lazy Susan to cause it to propagate in the opposite direction in time. And then I'm going to rotate it back to the original position. All right, so what I've done effectively is I've gone from backwards back to forwards propagation. And what you would think is that you get the same result. Right? So my wave function will have this phase after I complete that 360-degree rotation. But you don't get that with a spin. When you rotate a spin 360 degrees and you measure its wave function, or if you represent its wave function, so you get the opposite phase. You get a negative sign. So 360-degree rotation of a spin, so 360-degree rotation of my electron wave function gives me minus the electron wave function. It flips the sign of the wave function. So in order to get back to my original propagation, which is the phase of my orange wave, my original electron wave, I have to rotate the system twice. That does not work. Now for a normal object that's propagating like that has some helicity like this, right? Like an electric field, you don't need this. You rotate an electric field that has some polarization, some angular behavior, rotate it 360 degrees, you get the same wave that you had at the beginning. But with spin, you get a negative sign. So you need 720 degrees of rotation in order to get back to the original state. Don't have to worry about that, but this is why this doesn't work. Is that there's an extra symmetry, an extra geometry to spin that's deeper than 3 dimensions. Right, the three-dimensional rotation gives you side. If you rotate anything in 3 dimensions 360 degrees, you get the original thing back. Right, that makes sense. But in spins, you have to rotate it twice to get it back. Very, very interesting. Deep, deep consequences for a lot of different things. All right, and this is intrinsic to the geometry, what we call the geometry of spin, the geometry of physics at the subatomic scale. Things don't always give you the same thing back when you rotate around a circle. In some ways, spin is like a spiral or a Mobius strip. It requires 2 rotations to get back to the original point. It's very, very complicated. And we're never going to worry about this, but I think it's important to note that this is, right, that spin is unique to quantum mechanics. There's no analog to it in normal day life. All right, so I have like 10 minutes left. I just want to close this conversation up a little bit with just a few more examples of spin, right? And then we'll hold off on applying this to the hydrogen atom then when we get to the hydrogen atom. Once we start talking about orbitals and stuff, we'll come back and start thinking about how the spin may affect things. It's important to know that the electron has spin. This is an angular momentum the electron always has. And so you can imagine, what if my electron is in a p orbital where it has angular momentum around my proton? Right, it's rotating. That electron also has spin angular momentum that's there as well. So what does that mean? That means that the electron, which is orbiting, is also orbiting itself, right? It also has some angular momentum, intrinsic angular momentum to itself, right? So the electron, you can kind of think of it this way, is that the electron and the proton aren't tidally locked, and that the electron is always facing the same way with respect to the proton. Of course, the electron is a point and spherically symmetric. It's meaningless. But it's not like the moon and the Earth where there's a dark side of the electron and a light side of the electron compared to the proton. They're not tidally locked to each other. But rather, that object is rotating as well. Well, when you rotate something in orbit with something else that's rotating, those 2 angular momentum can add and subtract to each other. So what we're going to find is that the spin of the electron affects the angular momentum of the electron around the proton. All right? And that's going to cause some changes to the energy levels of the hydrogen atom and make our energy level structure a little more complicated. And this is completely observable. Right? When we talk about the 1s orbital and the 2s orbital and the p orbitals and stuff like you do in Gen Chem, that's an approximation. You're ignoring spin. That's assuming there is no spin. But when we add spin, we're going to realize that you can add the orbital angular momentum constructively with the spin, or you can add it destructively from the spin, and that's going to have 2 different energies, and every level of the hydrogen atom is going to split into 2. One where the angular momentum of the electron, orbital angular momentum of the electron, is in time or in space or constructively interfering with the spin. And then there's going to be a state that's higher energy where the spin is opposed opposite to the angular momentum. It's going to be higher energy. So every level is actually split. And it wasn't until the 1920s or so that people actually discovered this. Right, it's called spin-orbit coupling. It's a super important thing in all atoms, and we'll talk about it once we get to the hydrogen. Right? So this will have consequences for us. The spin of the electron affects the structure of the hydrogen atom directly and measurably. So let me just add one more thing. Let's just look at one more particle, and then I'm going to close up shop. Let's look at the photon. All right, the photon doesn't have mass. It does have spin. It's spin 1. In fact, it is one of the only fundamental particles that has an integer spin. All right, of all the particles that exist at normal energies, things in the standard model, things that we talked about in the first week of class, photon's one of only 2 major fundamental particles that has a spin that isn't a fraction. All right, we'll see what that means in a second. The other one is the Higgs boson, which is spin 0. So the photon's about the only one that has an integer spin.
And You said it was 2?
It's 1, sorry. That's a bad 1, I apologize. Does that look more like a 1 to you?
Yeah.
Okay, it's spin 1. So that means that S is equal to 1. Right? And what does that mean M can be? Well, M can be -1, -1 plus 1, that's M equals 0, or M equals 1. Right? So a photon has 3 spins, 3 different spin states. Now we can interpret -1 and 1 as it having some helicity, right? What that means is that if you think of the photon as a wave, let me again, my propagation axis is like this, right? You can think of the photon as a wave propagating across space. So here's my wave function for my photon, my wave, right? -1 means, again, clockwise rotation around the axis. Right? The wave is rotating like this. The wave front rotates clockwise, or counterclockwise. Did I have that clockwise? Sorry, that's counterclockwise. I apologize. I have it flipped. It doesn't really matter. It's clockwise. CW. All right? Right? We call this right-handed circular polarization. If you've ever used polarized sunglasses, the reason why they make things darker than unpolarized sunglasses is because they block circular polarized light. If you have light rotating like this and your polarizer is the opposite direction, it wants left-handed light instead of right-handed light, it blocks all the all the photons of the opposite handedness. So polarization does. Right, so we have this circularly polarized light, and equivalently, we have left-handed circular polarized light. I think I flipped my right and my left. I apologize. I think this is left. Yeah, this is left.
Wait, what?
Left-handed polarized light. Right, because it's like this. My left is the propagation vector is this way, and it's left-handed, then that means it's going to rotate clockwise.
Okay.
Right, so left-handed. Right-handed would be counterclockwise. Right, so I always get that fixed up. Yeah, so the right-handed rule. It's a stupid rule, but unfortunately it's useful. So M equals 1 is counterclockwise rotation. This is right-handed circular polarization. All right, and M equals 0 is no polarization at all. It's just a wave moving across. There's no rotation at all. It's just a wave propagating linearly. Right? You can make light sources that generate well, you can't generate left or right uniquely. That's very hard. But you can generate linearly polarized light sources and circularly polarized light sources. A laser is a linearly polarized light source. There's no rotation in a laser. Laser, all the photons move in the same direction. You can make a circularly polarized laser, I guess. But most lasers are linearly polarized. All the vectors of all the photons are all moving in the same direction. They have no helicity. They're just a straight beam of wave. Right, but you can make circular polarized light sources all the time. People use them in infrared spectroscopy. There's a technique called circular dichroism where they use circularly polarized light to detect chiral molecules. Right, you can make circularly polarized light and linear polarized light with filters and polarizers and all sorts of stuff. Right? You can use optics to take advantage of the different spins of the photons, and they have different properties. Right? And it's entirely intrinsic to the photon. Okay. There's one more feature I want to mention, but I don't have time, so we'll come back to it on Tuesday. One more comment about particles with spin. I haven't distinguished between particles of fractional spin and integer spin. So we'll have to come back to that. There's a difference between the two, but we'll talk about it next class. Not too big right now. All right, you guys have a good day. Homework, our exams due tomorrow night. I will have my office hours tomorrow at 11:30 as usual. If you have any last-minute questions, you can come talk to me. Otherwise, have a nice weekend.
I haven't started the exam yet. I guess it's shocking. I haven't started the exam.